Alright, on this problem we're told that a student's measuring a magnetic field with a magnetic field probe, and he's measuring it around a current carrying wire. Now you're told that the current goes into the page, so you have to use your first right hand rule to find the direction of the magnetic field at the probe. So if you take your thumb, remember the thumb is directing the current, put it into the page, then over here at the probe your finger should be pointing down. So your direction of your magnetic field here. So the direction of your magnetic field here should be going down, like I have drawn. Now, you're told that the student forgot about the Earth's magnetic field, which has a value of 5 times 10 to the negative 5 Tesla, and this location is pointed north, which means the Earth's magnetic field here is going to be pointing up this way. Now, since magnetic fields are a vector, you take the difference in them. So what the student really measured in his graph was, since they're pointing in opposite directions, was his wire's magnetic field minus the Earth's magnetic field. And since we want to just have the wire, we have to get rid of this Earth's magnetic field here. So when you take the wire minus the Earth, what you're basically doing is subtracting this 5 times 10 to the negative 5 Tesla each time. So to get rid of it, we want to add it back in. So on this graph, what I do is I just put a point, 0.5 times 10 to the 4th, or 5 times 10 to the negative 5th, above each one of his spots. And when you combine them together, you get this new line. Alright. The next thing it says is to calculate the value of the current in the wire. So what I'm going to do is I'm going to choose one of my points. I chose this point right here because it actually happened to be on a line. And I'll use the values of that point to determine my field. Now, I know the magnetic field around a current carrying wire is given to me by the formula that B equals mu naught I over 2 pi r. And I'm given the value I. I'm looking for the value I. And I'm given the value field from the graph and radius from the graph, and mu naught as a constant. So if I plug in my value of magnetic field at that point, which was 5 times 10 to the negative 4th Tesla. That's just the point I circled on the graph a minute ago. Which equals mu naught. Mu naught is 4 pi times 10 to the negative 7th Tesla meter per amp. 4 pi times the negative 7th. That's a constant. Looking for I. And 2 pi, and my radius is given to me as, at that point, is 0.02 meters. So if I solve for I, this point works out rather well. You should be somewhere around 50 amps. If you're anywhere in that range of 50 amps, then you'll be fine. All right, on the back. So there's another student who does not have a magnetic field probe, uses a compass and a known value of the Earth's magnetic field to determine magnetic field generated by the wire. With the current turned off, the student places the compass from the wire, and the compass points directly toward the wire as shown. That means that the wire is going north, the compass is pointing north, and the wire is above it. So the first thing you want to know is sketch the direction of the needle points after the current is established. So if we have our compass, or we have the point where our compass is, and we have this right here is north, we know that the Earth's magnetic field is going to point north, because it's told to us in the problem. Earth. Magnetic field points north. Now, since we have a wire up here, let's do this right here is our wire, and the current goes, I believe it goes into the page, yes, into the page. So if you take your thumb, point into the page, down here at your compass, your finger should point to the right. Now, the compass will not point directly to the right because there's the Earth's magnetic field, but it won't point directly north because there is the Earth's field. And by right, I mean west. It's kind of backwards when I have to draw it on here. So our needle will actually be the vector sum of these two things. So if we have our compass, the needle will point somewhere in between the north and the west axis. Somewhere in between there. Where this right here is an angle theta, which you have to find in the next problem. So we had to find this angle theta by looking at basically vector addition. First thing we need to do is figure out what the field of the magnetic field is at the wire. So we do this with our B equals mu naught I over 2 pi r formula that we used just a minute ago. So we're looking for B this time. Mu naught is 4 pi times 10 to the negative 7th Tesla meter per amp. I is given to you as 35 amps, and 2 pi's number, and r is 0.04 meters. If you plug this in, you get that the magnetic field is 1.75 times 10 to the negative 4th Tesla. Now, that's important, because if you look at your compass, we have this right here, this 1.75 times 10 to the negative 4th Tesla pointing this way, and we have this Earth field of, it was given to you in the last problem, 5 times 10 to the negative 5th Tesla going this way. Now, if we want to figure out what the angle is, we have to add these up via vector addition. And when you add it via vector addition, you add these things head to tail, which means that my Earth's vector needs to be put at the tail of my other vector. That should not be an arrow, that's wrong. This right here is 5 times 10 to the negative 5th Tesla. And then the resultant direction will be the hypotenuse of this triangle. We were asked for this theta right there. Now to find this theta, I know the opposite, I know the adjacent, so I can just find the tangent of this angle, where tangent of theta is going to be opposite of adjacent. Y'all know I love some tangents because they make the world work. Not really, but they make math nice, and I get pictures of them. So that's my opposite. My adjacent is going to be 5 times 10 to the negative 5th Tesla. I'll get rid of this right there. And if you take the inverse tan of 1.75 times 10 to the negative 4th over 5 times 10 to the negative 5th, you should find that the theta of this is 74.05 degrees, which means this angle is going to go from being up here north down to 74.05 when it has both these magnetic fields acting on it. Alright, this says that the wires now is part of a circuit. Well, it's always part of a circuit, but it's connected to a power source with a voltage of 120 volts and a no internal resistance, and asks you to calculate the total resistance of the circuit. So for this right here, we just go to Ohm's law. V equals IR, where voltage is given to is 120 volts. Our current is told beginning is 35 amps. And we're looking for the resistance. So solve for R, 120 divided by 35 is 3.43 ohms. And then it says calculate the rate at which energy is dissipated in the circuit. The rate at which energy is dissipated is measured in joules per second. We also know that as watts, and watts is power. So if we're looking for the power of the circuit, power is equal to IV. Our I is 35 amps. Our voltage is 120 volts. I cannot write A. And if we solve this, 35 times 120 is going to be 4,200 watts, or 4,200 joules per second. Either way will work.